Dear students, today I am going to explain about inference rules, equivalence and minimal cover. After that we will discuss about normalization algorithms. First we will see inference rules. Inference rules for functional dependencies. So first already we have discussed about what is meant by functional dependency, what are the different types of functional dependency in the previous class. For example, if each department has one manager, the department number defines manager SSN, manager SSN defines manager phone, then these two dependencies together imply that department number defines manager phone. Okay. So this we have seen in the transitive dependency. So that is now the new dependency department number defines manager phone is inferred from the other two dependencies. So that we are going to see with the rules, inference rules. Before that we will see it is a useful to these inference rules are useful to define a concept called closure. Formally that includes all possible dependencies that can be inferred from the given set F. Okay. First, closure of F denoted by F plus the set of all dependencies that include F as well as all dependencies that can be inferred from F is called closure of F. Okay. So, that closure of F is denoted by F plus that includes the given functional dependency F and all other functional dependencies inferred from F. So, before seeing that closure of finding the closure of algorithm, we will see what are the inference rules are there. Okay. To determine a systematic way to infer functional dependencies, we must discover a set of inference rules that can be used to infer a new dependencies from a given set of dependencies. Armstrong's inference rules, so first there are 6 rules. The first rule we will see IR1, inference rule 1, that is called as reflexive rule. What is that reflexive rule means? If y is subset of x means that we are going to represent like this, x, that is y is a subset of x, then x defines y. If y is a subset of x means then x defines y. Then next rule IR2, inference rule 2 is called as augmentation rule. This rule states that if x defines y, then we can add additional attribute on both the sides, xz defines yz. Okay. So, this notation normally we are using the union operation. Okay. X union z. Then next rule, third rule is called as inference rule 3 is transitive rule. That already we have seen, if x defines y and y defines z, then x defines z. So, these 3 rules are called as reflexive, augmentation and transitive rules are called as sound and complete set of inference rules. These are called as a sound and complete set of inference rules. So, along with that there are other 3 additional rules are there. The fourth rule is called as decomposition rule. Okay. Already we have seen that augmentation rule. Now we are having decomposition rule. If x defines y, z means we can write that x defines y and x defines z. We are decomposing that y z into separately y and z. X defines y and x defines z. Next IR5, inference rule 5 is called as union rule. That is, if x defines y and y defines x defines z, then x defines yz. The right hand side we are joining, making union. Then next is IR6 is called as pseudo transitivity rule. That rule states that if x defines y and y defines z, x defines y and y defines z, y and more this is added z, then wx defines z. That is pseudo transitivity rule. Okay. The last 3 inference rules as well as any other inference rules can be deduced from inference rule 1, 2 and 3. Okay, that is why it is called as a complete and sound. A functional dependency x defines y is trivial if y is a subset of x, otherwise it is non-trivial. So, if functional dependency x defines y is a trivial functional dependency when means if y is a subset of x, Otherwise, it is called as a non-trivial functional dependency. I think now you can be maybe clear about inference rules. There are 6 inference rules. Among that 6, the 3 rules are main thing: reflexive rule, augmentation and transitive rule. Then other 3 rules are decomposition, union and pseudo transitivity rule. And we have seen what is trivial dependency and non-trivial dependency. Next, here there is closure. Closure already know. Closure of a set F of functional dependencies is the F plus of all FDs that can be inferred from F. It not only includes all the FDs inferred from F, this also includes the original functional dependency F. Okay. So, that how we can determine means X plus can be, there is closure of set of attributes X with respect to F is the set X plus. X is a attribute set of all attributes that are functionally determined by X. So, now X plus can be calculated by repeatedly applying inference rule 1, 2 and 3 using the functional dependencies in F. So, for example, the algorithm for determining X plus, that is the closure of X under F. So, what is the input means? A set F of functional dependencies on the relation schema R is given as an input along with the set of attributes X, with that X is a subset of R. This will be the input to this algorithm. Then X plus is equal to X. Initially, the given attribute X is assigned to X plus, then repeat, that is X plus is assigned to old X plus. Okay. Then that is for each functional dependency Y defines Z in F, do, then if X plus is a subset, that is Y is a subset of X plus, then X plus is equal to X plus union Z. Okay. Until X plus equal to old X plus, that is until we are adding all the attributes in that thing. So, we have to apply these steps, continue repeatedly, and we have to find out the closure of X under F. Okay. So, for example, here given the relation, the same example, we are determining the X plus under the closure of X under F. So, we are having the relation R with the attributes A, B, C, D, having the functional dependencies A defines B, C defines B, D defines E and E defines D. We will take one by one each and every attribute. First A will take means A plus we are finding according to that rule that A defines A itself, A, and also A defines B and C. So, A, B, C. So, then no other way that is defined. Then B will take, B defines nothing here. So, B plus is equal to B itself. If we will take C, C defines B, but no other way. So, C plus is equal to CB. And if we will take D, D defines E. So, D plus is equal to D comma E. And if we will take E, E defines D, then E plus is equal to E comma D. Okay. So, here we will take all the X pluses there here, but no X pluses includes all the attributes in a relation. So, we can make, not to find out the key, candidate key, we can combine the two X plus, that is, suppose for example, we need here how what are the attributes are there, A, B, C, D and E. Here I missed that E is there. So, here E you should please include that E. So, A, B, C, D, E will take, then A, suppose we will combine A and D, we will get A, B, C, D and E. And same time A, E and we will combine A plus and E plus, we are going to get A, B, C and E, D. So, these two are the candidate keys. Okay. So, like this we have to find out the closure of X under F. Okay. So, this problem do not confuse it. The relation R contains the attributes A, B, C, D and E. Okay. So, the next class we are going to see some more concepts about equivalence relations and minimal cover.